All around us, every single second, the world is changing, right? Things burn, things rust, they grow, they dissolve. But you know what? It's not magic. These are all chemical reactions. And today, we're going to pull back the curtain and learn the secret language that chemists use to describe exactly what's going on. I mean, we've all seen a rusty pipe, probably a million times, and didn't think twice about it. But if we could just zoom way, way in, down to the molecular level, we'd see this incredible transformation taking place. You've got shiny iron atoms literally grabbing oxygen right out of the air and rearranging themselves into a totally new substance, iron oxide. We just call it rust. That's a chemical reaction, happening in plain sight. So think about this for a second. A rusty pipe and a burning fire. One happens super slow, over years, and the other happens in a flash of heat and light. What on earth could they possibly have in common? Well, they're both chemical reactions. They're both processes where things are fundamentally, completely changed. And to really get a grip on them, we need a way to write them down. And that is where the chemical equation comes in. The best way to think about it is like a sentence in a brand new language. On one side of the sentence, you have your starting ingredients. We call those reactants. And on the other side, you've got what you end up with, the products. The equation tells the whole story of that change. This is what that language is actually describing, on a scale that's totally invisible to us. Here, you've got some hydrogen and oxygen molecules just kind of floating around, but when they get together and react, their atoms do this complete reshuffle to form something entirely new, in this case, a couple of water molecules. And here is how we write that sentence down. This is the chemical equation for what we just saw. Over on the left, we've got our reactants, 2 parts hydrogen plus 1 part oxygen. That little arrow in the middle, you can just think of that as meaning turns into. And on the right, our product, 2 parts water. Those little letters in parentheses, by the way, they just tell us if we're dealing with a gas or a liquid. Now, like any language, this one has rules. And there is one really, really important rule. It's not just a chemistry rule, it's a fundamental law of the entire universe. And, as a certain big purple guy once said, everything must be
perfectly balanced. This is the law of conservation of mass. It sounds complicated, but it's actually super simple and totally non-negotiable. You can't create atoms out of thin air, and you can't make them just disappear. All you can do is rearrange them. So whatever atoms you start with, you have to end up with the exact same number.
And there you have it. The universe itself demands balance. So in chemistry, that means our equations, our chemical sentences, have to be balanced. The number and type of atoms on the left side have to perfectly match the number and type of atoms on the right. Let's go back to our rust example. If you look at the unbalanced equation on the left, it's basically lying to us. It's saying 1 iron atom magically turns into 2, and that just breaks the number 1 rule. To fix it, we add what are called coefficients. Those are the big numbers out in front. Now look at the balanced equation on the right. It correctly shows us that 4 iron atoms react with 3 oxygen molecules to make 2 units of rust. Now everything is accounted for, perfectly balanced. Okay, so we get why we have to balance equations. It's a law of the universe. But how do we actually do it? Don't worry, it's not as scary as it looks. It's really more like solving a little logic puzzle than doing hard math. So here's the basic strategy for solving the puzzle. First, you just write down all the pieces you're starting with. Now, here's a pro tip. If you see big chunks of atoms that appear on both sides, we call those polyatomic ions, just treat them as one single piece. It makes life way easier. Next, you go for the easiest targets. Find the elements that only show up in one spot on the left and one spot on the right. Start balancing those by changing the big numbers in front, the coefficients, until they match. Then you tackle everything else, and at the very end, you do a quick final count to make sure all adds up. Now, you might be thinking there are millions of possible chemical reactions out there. And you'd be right. But here's the good news. Most of them fall into just a few basic categories. You can actually think of them as the 5 basic plot types for chemical stories. First up, we've got synthesis. This is the getting together story. It's a classic romance plot. You start with 2 or more simple things, let's call them A and B, and they combine to form one more complex thing, AB. Simple as that. And hey, look who it is, our old friend rust. The formation of iron oxide is a perfect example of a synthesis reaction. You have simple iron and simple oxygen, and they combine to make the more complex iron oxide. It totally brings our first example full circle. Next up is decomposition.
This is the breakup story. It's the exact opposite of synthesis. Here, you start with one complex thing, our couple AB, and something causes it to break down into its simpler parts, A and B. A really powerful example is when you run electricity through water. That process is called electrolysis, and it gives the H2O molecules the energy they need to literally break apart into what they were made of, hydrogen gas and oxygen gas. One complex thing breaks down into two simpler things. That is decomposition. The other three basic plots are just as easy to spot. In a single replacement, it's kind of like a solo element cuts in on a dancing couple and swaps places. In a double replacement, you have two couples on the dance floor, and they just decide to swap partners. And finally, you've got combustion. That's the action movie plot. It's the fiery one. That's when something burns by reacting really fast with oxygen, creating heat, light, and usually carbon dioxide and water. Okay, let's add one more layer to this. A huge number of chemical reactions, probably most of them, don't just happen in the air or in a solid block. They happen when stuff is dissolved in the most common solvent on the whole planet, water. When something is dissolved in water, we give it a special name, an aqueous solution. Water is the solvent, that's the stuff doing the dissolving, and the substance that gets dissolved, like salt, is called the solute. Simple enough, right? But what's really happening to that salt when it dissolves is pretty amazing. And this right here is the absolute key. For a lot of compounds, dissolving isn't just mixing. It's called dissociation. The compound literally breaks apart into tiny charged particles called ions. So this potassium sulfate solid doesn't just float around as a whole unit in the water. No way. It splits into separate charged potassium ions and sulfate ions. And because these charged particles are now free to roam around, well, they're ready to get into all sorts of new reactions. Okay, so we've learned the language, we know the big rule about balance, and we know the basic story types. But there's one last really crucial piece to this whole puzzle. Just because you can write an equation on a piece of paper, does that actually mean the reaction is going to happen? And this brings us to this huge concept. Just because you can write a perfectly balanced equation doesn't guarantee it's going to happen in the real world. Sometimes the reactants just sit there next to each other, doing absolutely nothing. They need a reason to react, a push, what chemists call a driving force. So that's really the final question, isn't it? What is it that gives a reaction the push it needs to actually go? Is it the fact that a solid forms, or that a gas is released, or maybe that electrons get transferred from one thing to another? Understanding these driving forces, the real reasons things burn and rust and grow, that's the next step to becoming fluent in chemistry's secret language. And that's a story for another time.